So welcome to this uh, lecture on closed operators. We have seen before compact operators, and this is another family that is different from continuous operators. Closed operators, as we can see, we'll see, are somehow a bigger family than just continuous, therefore bounded operators. So it contains also, there are examples of unbounded operators, which are closed operators, and we'll see some of their properties, especially when it comes to projections. Okay. So first, in order to define closed operators, this is first throughout we'll assume let x and y be two normed vector spaces. Let us consider the product space. Okay, and we will see that this is a norm is a normed vector space, and one way to do this is to take R2, to take a norm on R2, and from that norm on R2 generate a norm on X cross Y. But since all the norms on R2 are equivalent, so we'll take by the norm by the norm. So this would be norm of XY throughout would be the norm of X in X plus the norm of Y in Y. So we are taking the L1 norm, but we could have taken the max, the norm 2, etc., etc. But we'll take this norm. Let M be a subspace of X. Okay. And let A be defined from M into Y be a linear operator. If we did not have a subspace, we can consider any operator. It doesn't have to be a linear operator, so because we need to have linear behavior of A. That's why we're taking M to be a subspace. Okay, the domain of A is a subspace of X. Okay, then we define the graph A to be the set of X, A of X. X belongs to M in the domain, and this is a subspace of X cross Y. Let us take now the following definition now. Definition. A is said to be closed if and only if the graph of A is closed in X cross Y. So an operator is closed if and only if its graph is closed. Okay. So remember what the closed graph theorem says. If you are in a Banach space, okay, and you are defined on the entire Banach space, on a Banach space, if the domain is a Banach space, then the linear operator is continuous if and only if it is its graph is closed. Okay. Let us state the following result, which is very interesting because it helps us decide when an operator A is closed. So we have the following sequential characterization. Theorem. Let X and Y and M as before So X and Y are normal vector spaces, and M is a subspace of X. So we take now an operator A that goes from M into Y, be a linear operator. Okay, A is closed if and only if for any sequence xn, for any sequence xn in M, such that limit of xn equal x exists, and limit of t of xn when n goes to exists, so both limits exist, then t of x equals to y. Okay, this sequential characterization it will be very, very helpful to prove some nice results about closed operators. So it will be very handy. Okay, instead of going to the graph, we can just use this sequential characterization later on. So proof, this is just, it's a simple proof, not very complicated. This so assume A is closed. Assume first T, sorry. What did we call it? Was it? It's an A. It's an operator A. So sorry. So here, okay. So this is A of xn, A of x. This is operator A. So assume A is closed. Then the graph of A is closed in the product space. Now let xn be in M such that limit of xn equal x and limit A of xn equals y when n goes to infinity. Both limits exist. Okay? So now it's easy to see that limit of xn A of xn is equal to xy in the product space when n goes to infinity, and this is true in the product space, since xn A of xn are in the graph of A, so their limit, so xy belongs to the graph of A bar. Okay, in the closure of the graph, since A is closed, the closure is equal to the graph, because we have the graph is closed. Okay, so x, y belongs to the graph, which gives that y equals A of x. Okay, great. Now, conversely, assume the sequential condition on A. Let us prove that A is closed. So we want to prove that the graph of A is closed. Okay. So in order to do this, let us prove that the graph of A is closed. Okay. Let xy belongs to the closure. There exists sequence xn a xn in the graph A such that limit of xn a xn equals xy when n goes to infinity. So using the L1 norm, for example, then we have the components also, they do converge, so limit of xn equal to x when n goes to infinity, and limit of a of xn is equal to y when n goes to infinity. Now the sequential condition, so the sequential condition satisfied by A implies y equal a of x, which means that xy belongs to the graph of A. So the graph of A is equal to the graph of A closure, which means the graph of A is closed. So the graph of A is closed, which means A is a closed operator. It is clear from this sequential characterization that it is clear that if if A is continuous, then A is closed. So theorem, let us see when the converse is true. In other words, when a closed operator is continuous. And as I said, if you want to use the closed graph theorem, you need to have some kind of completeness somewhere, okay? So here, this explains why we have this assumption that x and y be Banach spaces. Let M be a subspace of X and A goes from M into Y. Okay, so be a linear operator. If the domain M is closed, okay, subspace of X, then A is closed if and only if A is continuous. Okay, proof. Since M is closed in a Banach space, then M is a Banach space. It's complete. A Banach space. So our operator now is dependent on a Banach space. And we know that A, which belongs as a linear operator from M into Y, is continuous if and only if, this is of course a property of the closed graph theorem, if and only if, is continuous if and only if the graph of A is closed. So this is exactly the conclusion of the closed graph theorem, which means that this is true by definition if and only if A is closed. So in this case, closed operators and continuous operators are exactly the same. So in the case of bijections, we have a beautiful result. Okay, so here, theorem is invertible operator, let x and y be two Banach spaces, let M be a subspace, okay, let A go from M into Y be a closed linear operator. So keep in mind, we are not assuming that M is closed, to be able to have that A is continuous. But what we assume is, that the inverse going from Y into X exists. So this happens if A is what? Surjective and injective 1-to-1, and surjectivity means that the range A of M is equal to Y. Okay? So in this case, we are assuming that the range is the entire Y, which is a Banach space. I mean, we can weaken this by assuming that A inverse goes from the range of A into M, but we have to assume that the range is closed. Okay? If the range is closed, we'll have the same conclusion. Then A inverse is continuous. Okay? Proof is very easy. Okay? Following the previous theorem. So we have the domain, okay? A inverse is defined on Y, which is a Banach space. Okay, number one. So the domain is closed. And the graph, so we have the following. So the graph of A inverse is equal to Y A inverse of Y, Y in Y, which is exactly the inverse. Okay, so here we have A of X, X belongs to M. Okay? So it's a reflection of the graph of A. That's exactly the graph of A inverse. So since the graph of A is closed, then the graph of A inverse is also closed. So now, of course, we have what? We have the graph, closed graph theorem applies that then A inverse is continuous. Okay, let us just make a quick remark here. What if we don't assume that A inverse exists from M into Y, and that A inverse only exists between the range of A into M. So in this case, what we can show is that A closed will imply that A inverse is closed. So we'll have now that A inverse is closed operator, not continuous operator. Okay. Let us have an example of a closed operator which is not continuous. Okay. So let's take x equal y equal continuous functions on 0, 1 with the sup norm. So definitely these are Banach spaces. And let's take M to be the subspace of X, which are F in C of 0, 1, such that F prime also exists and belongs to C of 0, 1. So we have what we call C1 of 0, 1. Okay, so the functions do have first derivative, and the first derivatives are continuous. And let's take now the operator. Let A go from M into C of 0, 1, where we take F gives F prime. So we take the differential or the derivative operator. Then A is linear. A is linear. Okay, but A is unbounded. We have seen this example before, and the example, take Fn equal Fn of x equal E minus nx. Okay, so we get that the norm of all the Fn's is equal to 1, and the norm of A of Fn is equal to m. So the sequence is not bounded. As we said, you have a bounded sequence, but its image is unbounded. Okay? Let us show now, that A is closed. Okay? So let Fn be in M such that, number 1, limit of the Fn's equal to F when n goes to infinity, and 2, limit of Fn prime equal to H when n goes to infinity. So for the sup norm, in the uniform convergence, we have the Fn which converges to F, and the Fn prime which converges to H. So what we're going to show, let us prove that H is in fact F prime or A of F. Let epsilon be positive. Okay, since H is continuous on 0, 1, then H is uniformly continuous. There exists delta positive such that for any x and y in 0, 1, absolute value of x minus y, okay, less than delta, imply that h of x minus h of y less than epsilon. Okay? Fix x and y such that x minus y less than delta greater than 0. Okay? So there exists C between Cn between x and y such that fn of x minus fn of y over x minus y equals fn prime of Cn. Okay, for every n. Okay, since this is for every n, for any n greater than 1, since the limit of the fn's, the uniform limit when n goes to infinity equals to f, then there exists n0 such that for every n greater than n0, we have the norm of fn minus f, which is less than epsilon. Okay? So now let n greater than n0. Okay? We have fn of x minus fn of y over x minus y minus h of x equal fn of x, I'm sorry, this is prime of Cn, the mean value theorem, Cn minus h of x, okay, which is f prime n of Cn minus f prime n of x, okay, plus no, not h of Cn plus h of Cn minus h of x. Okay, so we know that the absolute value of Cn minus x is going to be, because Cn is between x and y, is going to be less than the absolute value of x minus y is less than delta. Okay, so since absolute value of Cn minus x is less or equal than x minus y less than delta, we get absolute value fn of x minus fn of y over x minus y minus h of x less than the norm of fn minus prime h plus epsilon. Okay? And if we go back, since n, there was a little mistake here. Sorry. So here we have a mistake. Okay, let's go a little bit here. Sorry. I mean here prime. Okay? And if that's the case, then what we have here is h. So this will tell us prime and h. Okay? So this would be less than epsilon plus epsilon, 2 epsilon, because we choose n greater than n0. Right? So what does it say? It says here that for every epsilon we found n0 such that for any n greater than n0 we have fn of x minus fn of y over x minus y minus h of x is less than 2 epsilon. Okay? So if we let now n goes to infinity, let n goes to infinity, and we use now that limit, this is where we use the limit of fn equal f when n goes to infinity. So this is the uniform convergence. And if we have the uniform convergence, we have the pointwise convergence. So we get that the limit of fn of x minus fn of y over x minus y when n goes to infinity. So here, uniform convergence will give me 1 over x minus y limit of fn of x minus fn of y when n goes to infinity. And this is 1 over x minus y g of x minus g. I'm sorry, not g. f, okay, which is equal to f of x minus f of y over x minus y. Okay? So if we go back and choose the x and y such that the absolute value of x and y is less than delta, and we let n goes to 0, so we'll get absolute value of f of x. This is coming from this inequality right here. So this with this, so it becomes less or equal, properties of the limit on the real line, minus f of y over x minus y minus h of y, h of x, sorry, h of x. This is less or equal than 2 epsilon. So what we found, so this is for every x and y such that, okay, is less than. So if we let now, so what does it say? This it says a lot of things. Number one, that limit, so limit of f of x minus f of y over x minus y when y goes to x exists, and limit of f of x minus f of y over x minus y when y goes to x is equal to h of x. So the existence means that the derivative of f exists, and this is f prime of x for every x. So this tells us exactly what we wanted, meaning that f has a derivative, and this derivative is equal to h of x. Okay? So this was an example, beautiful example of an unbounded linear what? Operator which is closed. Now, another example of this, beautiful example, is the linear projections. Okay? So let us first recall what does that mean, a linear projection. So we have let x be norm vector space, or a linear, no. Let us just go back to the original linear vector space, because the definition has nothing to do with the has nothing to do with the normed or not. Let P go from x into x, be a linear operator. Okay, P is a projection if and only if P composed with P equal P. If and only if, what does that mean? It means for every x in x, P of x is equal to P of x. So that's the definition of projection. And of course, if you take out the word linear, then it becomes just a nonlinear or just projection. And so we do have the case of nonlinear projections. Not all the projections are linear projections, okay? So it depends on the case and on the examples. So we do have examples of nonlinear what? Projections. So nonlinear projections, this condition is still satisfied, okay? But we don't have linearity. Okay, so here, since we are dealing with linear operators, let us look at closely linear projections, and in a different lecture where I'll be talking about nonlinear projections and their properties. Okay, so here let's take two natural subspaces. Okay, so we have number one, the range of P. So that's R of P, which is P of X, X in X. That is the range. And if we look at the null space, okay, the null space of P, which is N of P, which is X, such that P of X equals 0. These are subspaces natural to any linear operator, but these natural what? Spaces, okay? So here we have the following. So first of all, theorem, okay? Let X be a linear vector space. Let P going from X into X be a linear projection. Okay. Then we have a natural decomposition. X equal R of P plus N of P. So the operator P leads to two subspaces which decomposes our linear vector space X. Okay? So proof, beautiful proof, simple proof. Let X belong to X, then P of X equals P of X, and since P is linear, then we get X minus P of X equals to 0. Okay, so which means that X minus P of X belongs to N of P. Okay, and since X equal P of X plus X minus P of X, we get that capital X is equal to the range of P plus the null space of P. So now what we need to do is to show that it's not just a sum but a direct sum. Okay, so for that, let us show that the intersection is reduced to 0, that X belongs to R of P intersect N of P. Okay, then there exists Z in X such that X equal P of Z. Okay, and P of X is equal to 0. So the first one, this here, because X belongs to the range, and this here, because X belongs to the null space. So P, okay, but P of X is equal to P of Z, which is P of Z, where we use the definition of the projection. So P of X equals to 0, because we said that X belongs to the null space and P of X is equal to 0. Okay, this shows what? Therefore, we have the intersection reduced to 0. Therefore, we have R of P intersect the null space is equal to 0. In other words, we have X is not just the sum, it is a direct sum of, so the decomposition is unique. That's the beauty of this, okay? Okay, great. A quick comment here. If you take a remark here, this theorem here is really beautiful, because this tells us how we can generate more and more more and more linear projections. So here, let X be a linear vector space. Okay. Let Y be a linear subspace. Okay. Using the concept of algebraic basis, just a DOM lemma, we can find there exists another subspace. There exists Z, a linear subspace of X, such that X, in fact, is the direct sum of Y and Z. So for every X, in X, there exists unique Y in Y and unique Z in Z, such that X is equal to Y plus Z. So if we put now P, let P go from X into Y, defined by X gives me little y, we see that P is a linear projection with the range of P equals to Y and the null space of P equals to Z. So you see, for every direct sum of the composition of the entire vector space X, we can come up with a linear projection. Okay? One more thing here, okay, to note, okay, another remark, okay, let X be a linear vector space, and P a linear projection. Okay, so very easy to check. It is easy to check that I, the identity map of X minus P, is also a linear projection. It's very nice linear projection. Okay, it's a linear projection. So, and moreover, we have that the range of P is exactly the null space I minus P, and the null space of P is equal to the range of I minus P. So in this case, we have that X is the range of P plus the range of I minus P, and it's also equal to the null space of P plus the null space of I minus P. And this, by the way, tells us also that the only possible eigenvalues of projections are 0 and 1. So n of P is the eigenspace associated to the 0 eigenvalue, and n of I minus P is just the eigenspace associated to the eigenvalue 1. So of course I'm assuming that they're not equal to 0, because if they are equal to 0, then automatically is not considered as an eigenvalue. Okay, so just connect it with the eigenvalues. Okay. So next we discuss topological properties. Topological properties of projections. Okay. theorem. Let X be a normed vector space now. Vector space. Let P, defined from X to X, be a linear projection. Okay? Then P, if P is a closed operator, linear operator, then R of P is a closed subspace of X. Okay? So, proof. Let Y belongs to the R of P closure. There exists Xn sequence in R of P such that limit of Xn and goes to infinity equals to Y. But since you belong to R of P, it's easy to check. It is easy to see that P of Xn is equal to Xn. So limit of P of Xn is equal to Y as well. Sequential characterization, since P is closed, okay, so the sequential characterization of closedness, closed operators, tells us that P of Y is equal to Y, which implies, obviously, that Y belongs to R of P. Okay? Of course, from what we learned before, if X is a Banach space, then P will be continuous. Let's go to the next result, because the next result discusses continuity. Okay, here, theorem. Okay, let X be a normed vector space. Let P of X into X be a linear projection. Okay. Then, if P is continuous, then R of P and N of P are both closed. Okay. If P is continuous, then obviously it is closed, and therefore R of P will be closed. And if P is continuous, we know that the null space is always closed. So there's no need to prove anything here. Okay? Okay? Theorem. Now the converse. We're going to be discussing the converse. Right? Let X be a normed vector space. Let P from X into X be a linear projection. Okay, assume that R of P and N of P are closed, then P is closed linear operator. Okay? Proof. Okay? Let Xn, we're going to use the sequential characterization of closed. Let Xn be in X such that limit of Xn equal X and limit of P of Xn equals Y. Okay? Great. So since P of Xn belongs to P of Xn belongs to R of P, okay, and R of P is closed, we get Y belongs to R of P. Okay? In other words, we have P of Y equals Y. Okay? Moreover, we know that X minus P of X for any X, Z, let's call it Z because we already used, belongs to N of P for any Z in X. So Xn minus P of Xn belongs to N of P for any n greater than 1. Okay? Okay? But the limit of Xn minus P of Xn is equal to X minus Y when n goes to infinity. Okay? Since N of P is closed, then X minus Y belongs to N of P. In other words, this implies P of X minus Y equals P of X minus P of Y equal 0. But we just said that P of Y is equal to Y, so P of X minus Y equals 0, or Y equals P of X. In other words, exactly what we wanted to show, that P is a closed operator. Okay? So now we want to have the converse to continuity, and for that we would like to use the previous result, and we know that in this case we need some kind of Banach, so we get the following theorem, the last result, theorem. Okay, let X be a Banach space, let P be a linear projection, assume N of P and R of P are closed, then P is continuous. So of course we know that P will be closed from the previous theorem, and the closed graph theorem tells us that P will be continuous because we are defined from X into X, and X is a Banach space. Okay, this is just the result that we saw before. So these are just some examples and some properties of closed operators. I hope you enjoyed the lecture. Thank you very much.